Hi, welcome to this tutorial on the working of our power supply circuit section. Here we will be learning the principle behind the working of our power supply section, which is actually a 5 volt DC power supply. So let us move on to our first section. So why do we need a power supply? Our project actually needs a 5 volt DC power supply because it works on the TTL level, and the mains power supply that we get from the power boards are actually 230 volt AC. So if we give those signals directly to our microcontroller and our project board, it will get damaged. So for that purpose we need a power supply section. Our power supply sections are stable because they had been designed so that they can convert the AC supply to the DC and also regulate it to a 5 volt level so that the microcontroller can work properly without any interruption. Because of their design, they are reliable. And again, because we need a 5 volt, we have designed it for 5 volt. If we need 12 volt, we can also design for 12 volt as per our needs. So now let us actually go to the power supply section and see what our components are there in it. The first comes the step down transformer. The step down transformer is actually a stepping down transformer. That means it actually steps down the 230 volt AC to 12 volt AC. Now how does this happen? There are actually windings in the transformer. We can say that it has a ratio of 230:12 so that the transformer can step down accordingly. So why do we need a step down transformer? A step down transformer is needed because it actually steps down the voltage given by the AC mains to the power project board. It actually, as shown in the figure, it converts from the input side the 230 volt to AC to 12 volt AC. How does this happen? Well, actually there are windings inside the transformer which are twinned around a copper core inside the transformer in such a ratio so that the voltage is electromagnetically coupled and also stepped down to the required voltage as per the design conditions. Also, the transformer is rated for a particular current. For example, we can have 500 milliampere transformer, we can have 1 ampere transformer, we can have 2 ampere transformer. For our need, we can change the transformer as per our needs. So now let us move on to this second component in the power supply section, that is the bridge rectifier. The bridge rectifier actually takes the input from the output of the transformer, that is 12 volt AC, to convert it to pure DC waveform. The bridge rectifier actually takes the AC input from the output of the transformer, that is 12 volt AC, and converts it to a pulse DC waveform, that is a 12 volt pulse DC waveform. Now let us see what happens and how it happens. Suppose we have the positive half cycle coming. So the positive half cycle is coupled over here, it is stepped down, and we have a 12 volt AC here, and the 12 volt half positive cycle has come over here, and it will go, because this diode has been now forward biased, the current will flow through this and go to the circuit load and then come back here, and now this diode is forward biased, and so it will come here, and in this way the circuit gets completed. So this was the positive half cycle, how we got the first pulse. Now let us move on to the negative half cycle. The negative half cycle is coupled over here, so we have this one as positive. So now as this point is positive, so this diode will be forward biased and the circuit current will flow this way and it will come back through here. And now since this diode is forward biased, it will come back here again, and in this way the circuit get completed, and we have the second pulse over here. So in this way the negative pulse is also converted into a positive pulse, and we have two positive pulses instead of a one full sine wave. So in this way we get a pure, not a pure, but a pulse DC waveform at the output of a bridge rectifier. But still we need a pure DC waveform for a proper functioning of our microcontroller based circuits. So again we move on to our next component which makes this possible. So we have this capacitor over here which acts as a filter. It actually filters out the ripples that are in the pulse DC waveform. How this happens, let us see. Whenever there is a pulse waveform coming, it charges the capacitor, and at the same time it flows to the load also. So actually the capacitor takes up the excess of the charge and gives the load a stable amount of charge all the time. You can see from the waveform over here what is happening. This is the waveform that is from the bridge rectifier, and this one is actually the waveform of the filtered waveform of the voltage. You can see that the waveform is more or less like a straight line. There are some pulses, but by varying the value of the capacitor we can vary the filtering process. So this is how actually the filtering process happens. Now let us revise how the things were going. We had a transformer that was converting from 230 volt to 12 volt AC. Then we had the bridge rectifier that rectified the AC signal to pulse DC waveform. Then we had the filter which was again filtering the ripples, filtering out the ripples, and thus we had a pure DC waveform which can be now given to a load. Now let us actually see in a simulation how these things are happening. So now let us see in the simulation section how the circuit actually works. So here we have a 50 Hz AC signal that will give 12 volt AC supply to our circuit. This supply is given to the bridge rectifier which will rectify the signal and give it to the load. So here we can see in color variations how the current is actually flowing through the circuit. We can follow the color schemes given here. So we can see that the green color, that when the positive pulse is passing, this diode gets activated because it is forward biased, and it flows to the circuit, and then this is given back through this diode and goes back to the supply. So this way the positive pulse is completed, and in the negative part again the another part gets activated and returns back to the other part and comes back to the supply. So in this way the pulse DC supply is generated by the bridge rectifier and given to the load. Now we will move on to the next section, that is the filter section, so that we get a pure DC waveform from this pulse DC waveform. Let us add a capacitor for this filtering process. So this is a capacitor. Now let us connect it with our bridge rectifier in parallel. Now as we see, the waveform is now changed. As it was pulsed before, it's less pulsed than before. So again we have a pulse DC waveform, but it is less pulsed. That means the width of the pulse is actually increased. That means it is approaching towards a DC signal. So what we can do is actually increase the value of our filter capacitor and observe the signal difference. Let us increase it by say 10 times. So we have 100 microfarad, and observe the signal. So we see that now there are variations, but they are too minor. So it has approached 90% DC. So it means that higher the value of the capacitor, higher the filtering process occurs. So let's again try to reduce the value to what was before. That is, let us now try with 0.1 microfarad, that is 100 nanofarad. So it has again changed it to a pulse DC waveform. That means the lower the value of the capacitor, the more the pulse DC waveform we will get from the output. That is just similar to as what we were getting with the bridge rectifier. So now let us try to increase the value of the filter capacitor to say 1000 microfarad, so that we will get a more better filtering. So with 1000 microfarad, what we can see that it has turned into a pure DC waveform. So we can conclude from this that the better the filtering process occurs at higher values of the filter capacitor. So in this way we get a pure 5 volt DC supply from our supply section, so which forms the heart of our project, because of which the project functions properly. So we will conclude this tutorial over here. Thank you for watching.